So in the interest of time, I'm going to talk about the hybrid ferroelectric and CMOS. And because of the excellent talk this morning by Professor Michael Lajevic, so I'll shorten. Originally, there are these points I would like to mention. Okay, so I'll shorten the motivation. I'll shorten also the hybrid flash memory. Okay, so we can leave more time to talk about the other sections. I apologize for that, just in the interest of time. Okay, so I'll jump through that. Why the hybrid ferroelectric and CMOS? The advantage, as laid out this morning, ferroelectric is a electrostatic control. It's compatible with CMOS logic today. Okay, it's just the switching is by electric field. There's no spin, there's no heat, there's no light, there's no migration necessary. There are no material integration for a long time, okay, because ferroelectric capacitor has been compatible to CMOS for at least 20, 25 years. And the domain switching of ferroelectric can be in the nanosecond range. The disadvantage is the FE capacitors. If you use the capacitor, ferroelectric capacitor, is less scalable because the readout current have to scale with the sensing circuit. Okay? And the short retention time in the gate stack, which will be more scalable, but then you will have to be designing the depolarization field very carefully in order for that to work. And lack of ideal ferroelectric materials until, for sure, the work by Professor Michael Lajevic and Mueller in 2011. Now we have this nearly ideal FE loop. Okay? When I say nearly ideal, the coercive field and the polarization, coercive field is close to the breakdown of the oxide, or how do you design for your silicon breakdown? And the polarization, it's close to your COX VDD. Okay, so now, before we're working with very tall PE loop, like PCT, or very flat PE loop, like PVDF, now we have square ones as well, okay, incomparable with the CMOS. It's interesting that the ferroelectric materials, even though the statics has been understood very well, the dynamics has not been, this is a static curve, and we know that this is caused by nucleations and the domain switching, okay? But how they really switch from one state to the other for the transient, it's problematic, okay? All the previous models has all the problems that to be implemented in SPICE-like simulator so that you can design your hybrid ferroelectric CMOS circuits, okay? So we try to improve from these previous models, okay, pre-stock models. This is a new technique about 2014 that people be able to observe how domain switching happen in real time. Okay, so it starts clearly from nucleation, then the domain grows. Okay, before it's a theory, now they can take pictures for that. Okay, so it's very clear how the ferroelectric material that they switch, start from nucleation, and then there's lateral growth of your domain switching. Okay. Now we can do a simple mathematical model, okay, for both the nucleations and how the domain can grow out of the nucleation. I won't explain the math, but this can be captured in the circuit model without a problem. Now you can see that during the dynamics of a ferroelectric switching have 4 distinctive stages. Okay, these actually have a lot of circuit implications. The first stage is just the lattice polarizations, and then it's dominated by nucleation, then go for domain switching, and then back to the lattice polarization again. Okay? So there are 4 distinctive states of ferroelectric domain switching, and we can capture that with an easy SPICE simulation. Okay. Once you have that, you can add your imprint, you can add your fatigue. Okay, those are all can be represented in the circuit model well. So now you can have a SPICE model, entirely continuous, no surprises in any region. You can deal with your ferroelectric hybrid CMOS. Let me illustrate just one circuit that this actually helps dramatically for the circuit. So the circuit I'm going to use is just the 1T, 1C ferroelectric capacitors. Okay, so let's look at, after we understand the dynamics, how can we design the circuits better? this actually has been presented many times for non-volatile logic, so that the ferroelectric can use this 1T1C and store the computing state in the ferroelectric. Okay? And this has been used in many, many different, especially mobile device like RFID or smartwatch, okay, using them as a non-volatile logic. So the traditional circuit is something like this. Okay? Traditional circuit is that you read out your state in your capacitors depending on what is the original polarization. Okay? So if you have to switch the polarizations, the readout current will be larger. If they're already in the one polarization, then the current will be smaller. And you use that current difference to latch it to your CMOS. Okay? So these are the curve that when you switch, okay, how the F and the F bar line switch for these two differential ferroelectric capacitors, so that depending on the storage, you will follow F bar and F will follow this line. The difference between these two is the memory window. And you can see that this is the dynamics. The window has a best place to be sensed. So how your latch is going to take that current difference, there's the best time to take it. If because of device mismatch, you take it in another place, you just have a smaller window to deal with. And your latch transistors also has mismatch, right? So if a failure can happen if you read in the wrong time, or is the wrong time, or this has mismatch, that this memory window is not large enough. And very simply, if you understand that this just from the previous four, the switching of this is still the four stage, the lattice polarization, nucleation, domain growth, and then lattice capacitance, then you can easily do a modification to these transistors. Instead of using a constant current source, okay, just give a current pulse. You can change the switching from this original to the F bar was switching the other directions. Okay, this resolves many problems because now I sense not using a constant current source to compare the current. I give a current pulse, then I can enlarge the memory window, and there's much more relaxation to the mismatch in your latch transistors. Okay, so these are just by showing that after we know the dynamics, then we can know how to design the circuits more correctly. Okay? So this is the part I'm going to skip. Okay, just follow Professor Michael Levick morning talk. Okay, just to mention. Okay, in the ferroelectric memory, actually there is a way to make it together with flash. Okay, and make it better. Okay, you can envision a hybrid device with ferroelectric and a flash memory charge storage, that the memory window from charge and polarization will be additive, program erase field can be additive, and the retention field is subtractive. Okay? These are possible. Okay? In the interest of time, I will not talk about this device. It's documented in the literature. It's just that when we do hybrid, we can really do hybrid. Okay? We can do flash and the ferroelectric hybrid. So let me switch to these have all the experimental results that the effect is true. I would like to switch, as this morning talk, at the last topic is about how ferroelectric work with the negative capacitance. Okay, let's take a look. This is the more controversial topic, and something now we understand how the ferroelectric switches. Let's take a closer look about this very, very important topic. So this is the negative capacitance is first presented actually quite early, 2008, that hoping to achieve sharper switching transistors without a memory effect. It's meant for a logic device. Okay? And it's the idea is just that the gate stack will have a ferroelectric and then a dielectric. Okay? So that's has been proposed for almost 10 years now, okay? Something that they hope to observe such a sharp switching. Indeed, initially, local sharp switching has been found experimentally. Okay, you can, in the 2 states of the switching, this is a PMOS-like switching, 6 millivolts and 2.6 millivolts per decade of current has been observed for local subthreshold slope. Although there is a 0.35 hysteresis, right? This one doesn't switch better in large signal than the MOSFET. Yeah. Oh, sorry. Okay. So now this is the theoretical best prediction. Okay. They hope to achieve this, right? So something that with a 0.15 volt switching, this is by Professor Hu in the 2015, saying that this, if we can achieve this, something this is a FinFET, that's the glorious device you have just heard, the FinFET can achieve, can we have something like this that have not only small signal sharp switching, but the on-off current state, maintaining 10 to the 6 on-off current state, but only use, say, 0.15 volts. Is that possible? Okay, so that will be the main topic I talk about. Okay, so if you and people saying that actually ferroelectric is the wrong thing. You should put anti-ferroelectric. A curve like have a 2. The curve is something like this: 2 openings instead of 1 openings. I'll take a look and say whether anti-ferroelectric will be better for this. Okay, and these are a long search for the experiments for can we have large signal sharper switching. Okay, up to today, nothing has been found experimentally. Small signal, many groups see it. Okay, small signal for switching, sharp switching on one side of switching, many groups have observed. But the goal is large signal on-off state, sharper switching. So let me give you the governing equations of this is your VG having an intermediate node across this ferroelectric, and this is your gate dielectric. Okay, so this very simple model used by all the NeurOhm MOS and the TP-MA, okay, all use the same model of this guy. Okay, so let's take a look. Okay, that whether this one, that your intermediate nodes can have a larger swing in the large signal sense than your VG by your ferroelectric capacitors. Okay? Once we have that, then every goal has been achieved. Okay? So if you look at the equations, yes, okay, the surface potential in your channel can be larger than this if you having this. This is called the temporary voltage amplification. You can switch, say, 0.2 volts and achieve 0.5 volts switch over there. Simply, sorry for this laser pointer thing. Okay, sorry. You can have a larger swing. Okay, and the difference of your improvement come for this. Okay, just from the NeurOhm MOS equations, this is your improvement. Okay, that the surface potential can switch more than your gate potentials. But let's look at every possible scenario, whether you work, okay? So if you have a tall PE curve, okay, you will see that this one, the VS, can be larger, but it's temporary. Because of the small coercive field, this one can be easily perturbed, okay? Also because of the small coercive field, it has to be very thick, okay, to be compatible with the CMOS you would like to do, okay? Something is, so achieving a correct capacitive ratio is difficult, okay? And if your PR, your remnant polarization is too large, it can be so large it can break your oxide, okay? So these are problems. So this one, but let's take a look seriously in here, okay? If you operate between these 2 points, then your VS can have sharper switching. But if you operate from these 2 points, okay, this lower corner to this corner, I call it the third quadrant to first quadrant symmetry, then the large signal is no better than just the equivalent dielectric. Let me repeat, this is a very central message, okay? If you have a PE message loop like this, then we're talking about large signal. It's not that this slope matters. It's where this state, the on state and off state. If the on state and off state is the same, then you draw a line here. Then your ferroelectric is not going to give you any better sharper switching, large signal sharper switching than just a pure dielectric with a dielectric coefficient just defined here. Okay. In the same argument, if you have a flat ones, okay, you will have all the even more problem, okay, because now you have a, even though the coercive field is larger, so that you're less subject to perturbations, but your remnant polarization is smaller, so the additional temporary sharper switching is smaller. How about the square? Okay, the square ones, it's a gray Hafnia, okay, ferroelectric compatible with CMOS, so all the aspect ratio will be correct. Okay, but if you have this first and third quadrant symmetric, okay, then this ferroelectric loop will be just the same as a dielectric response of these 2 points. So this will not work either. Okay, this will not give you large signal sharper switching. Okay, local you can, but when you switch back, the hysteresis pay back the penalty. How much penalty? It's just the same as if you replace your ferroelectric with a equivalent dielectric in the large signal. Okay, it's just where is your on and off points that's important. So does anti-ferroelectric works? Nope. It's here is that if you switch and passing this origin, and you can switch within this first quadrant, then it is like a dielectric is nothing but in here, right? So it's the end point and the on point and off point that's important. Okay, although you reap the advantage of now your electric field can always stay to be positive, and you can have a larger local sharp switch, but in the large signal, this one will still not give you the solution. Then what will work? Okay, this one will work. Okay, but it is a magic material. Okay, we don't know the material yet. Okay, if you have a PE loop like this, okay, a shifted ferroelectric, or it just a shifted, doesn't need to be ferroelectric at all. Okay, if you have a shifted dielectric like this, okay, then you can see that this one will be able reap the advantage of the additional 2P in your switching voltage. So this one will work, okay? But this one is not a ferroelectric material. Okay? No ferroelectric material can work in this, okay? In this way. And there's even this magic material exists. There's one additional problem. Let's look at if you switch from 0 volt to 0.2 volts to 0 volts, you hope your surface potential can switch from 0 volts to 0.5 volts to 0 volts to have a sharper switching on the silicon channel. Okay? Let's hold it. Okay? So hold the 0 volts to 0.2 volts and say this is designed correctly. This one switch 0.6 volt to 0.5 volts. If you hold it, right, remember this is a static CMOS, then it is inevitable you will have a depolarization field across this material. Okay? So this one will depolarize. Even though this, if you have this magic material, this one will have to be depolarized, right? So in the way of looking for the sharp switching large signal material, we need to find this material. And this material need to be able to counter the depolarization field of your voltage amplification. Okay? And this is not just a built-in electric field, okay? Because EP, polarization curve, is something called a intrinsic material variable. If in the device you put in a built-in field, it's really you are operating in a different domain of your PE. You didn't shift your PE, okay? Most MOSFET actually has been working with a built-in field called phi ms for the last 40 years. No negative capacitance ever being observed, okay? So this one is not just add in a phi ms, a built-in field, then all your problem will be solved, okay? It will not. Conclusion, okay? So the ferroelectric switching dynamics is understood. We have circuit model that for circuit designers, you can work with the dynamics of the ferroelectric switching and get predictive behaviors. the depolarization field plays a critical role. Okay? What is the electric field inside the ferroelectric material? Decide how domain switching in the desirable or non-desirable way is a very important consideration for your depolarization field. I say that so ferroelectric remain interesting, okay, but need the right material and the right circuits. Okay, I think we have both. Okay, the very last point, if you need a negative capacitance, then we really need these magic material that have the shifted polarization curve. Okay, I won't say it doesn't exist. It's just that that material hasn't been identified yet. Okay, it's not a ferroelectric, but hopefully that material can exist so we can enjoy a sharper switching switches. Okay. That'll be all my time.
Thank you very much.